Welcome students to the MOOCs lecture series on advanced probability theory. This is lecture number 5. In the last class, we have seen conditional probability and multiplication law. That is, probability of A intersection B is equal to probability of A given B into probability of B. In a very symmetric way also, we can write it as probability of B given A into probability of A. So, depending upon the situation, we try to obtain the probability of the joint occurrence of A intersection B. We shall see many problems later. Another thing we have seen independent events, that is probability of A intersection B is equal to probability of A into probability of B. When A and B are independent. What happens if A and B are not independent? Consider the example that I throw a die let A be the event that I get an even number. Therefore, probability of A is equal to the number of ways I can get even number is 3, because if the outcome is 2 or 4 or 6, out of 6 possible outcomes, therefore, this is half. Let B be the event that I get a number less than equal to 3. Therefore, probability of B is equal to number of ways of getting a value less than equal to 3 is 3, because I can get 1 or 2 or 3, which are my favorable outcomes, divided by the total number of possible outcomes, which is equal to half. What is probability of A intersection B? Now, A intersection B is the event that I get an even number less than equal to 3. Therefore, probability of A intersection B is equal to obtaining one even number less than equal to 3. That can happen only in one way, that is, if I get 2 divided by possible outcomes is equal to 1 by 6. Is it same as the product of the two individual events? No, because the product of these two probabilities is half into half, which is equal to 1/4. Thus, A and B are not independent. One should not confuse between mutually exclusive event and mutually independent events. Two events A and B are mutually exclusive if there is no omega belonging to omega such that omega belongs to A and omega belongs to B. Say for example, if this is my A and this is my B, then or their intersection is phi, therefore, these are mutually exclusive. But two events, say A and A complement any intersection, that is A intersected with A complement is equal to phi, always, right? But they are not independent. When we consider n events A1, A2, An, then they will be called mutually independent. If probability Ai intersection Aj is equal to probability of Ai into probability of Aj for all Ij belonging to 1 to n. Secondly, for all triplets, probability Ai intersection Aj intersection Ak is going to be probability of Ai into probability of Aj into probability of Ak for all I, j, k belonging to 1 to n, or in fact for any k of events that should happen. Therefore, we can write probability of a I 1 intersection a I 2 intersection a I m is equal to probability of j is equal to 1 to m probability of a I j, where each subscript belongs to 1 to n, and finally probability of a 1 a 2 a n is equal to probability of a 1 into probability of a 2 to probability of a n. Thus, we can see that mutually independence is a very, very strong relationship which needs to satisfy all these different equalities. Example. Suppose we have n boxes, each containing ten balls numbered 1, 2, 3 up to 10. Suppose one ball is drawn at random from each box. What is the probability that the largest number drawn is less than equal to 6, b the largest number drawn is equal to 6, and c the largest number drawn is greater than 6. So, these are three different events. Suppose we want to compute their probabilities. A, the event that largest number drawn is less than equal to 6 will happen if all the numbers drawn are less than equal to 6. Therefore, for each box the probability is 6 upon 10. There are 10 balls and I am looking at a number less than equal to 6. Therefore, it is coming out to be 0.6. Therefore, if AI is the event that the ball drawn from ith box is having value less than equal to 6, then the event A is A1 intersection A2 intersection AN is equal to, because they are now going to be independent, this is going to be A1 A2 into probability of AN, which is going to be 0.6 N. B. Event B is the largest ball drawn has value equal to 6. Therefore, this event can happen if all the balls drawn has value less than equal to 6 and at least one of them has value equal to 6. So, let A be the event that all balls have values less than equal to 6. Suppose this is the event, all values have less than equal to 6, and of which suppose a subset is that all values are less than equal to 5. Therefore, the probability of the event B is equal to 0.6 whole to the power n minus 0.5 whole to the power n. See, the event is that the largest number picked is greater than 6. This event is complement of the event that all the numbers picked are less than equal to 6. Therefore, probability of the event C is 1 minus 0.6 whole to the power n. So, these are some interesting way of solving some simple problems. Okay, students, with that let us proceed to study an important concept of probability, which is called Bayes theorem. It is important also, it is very useful for modeling many practical situations. However, before that, let us prove one theorem. So, let A1 A2 AN be n mutually exclusive events. Such that A1 union A2 union AN is equal to omega. Say for example, if this is our omega and I partition it into 4, this is A1, this is A2, this is A3, this is A4, and we can see that A1, A2, A3, A4 are mutually exclusive and their union is giving us omega. Then probability of any event A is equal to sigma probability of A given AI multiplied by probability of AI, I is equal to 1 to n. In this case, with respect to this example, suppose my event is this is my A, then probability of A is going to be probability of A given A1 multiplied by the probability of A1, probability of A given A2 multiplied by the probability of A2, and like that others. Probability of A is equal to probability of A intersection omega is equal to probability of A intersection A1 union A2 union AN. This is possible since AIs are mutually exclusive, is equal to probability of union over I is equal to 1 to n A intersected with AI is equal to sigma I is equal to 1 to n probability A intersected with AI. This is because we have already seen that these intersections are all mutually disjoint. Now, this is equal to sigma I is equal to 1 to n, and probability A intersection AI we can write it as probability of A given AI multiplied by probability of AI. So, proved. Example, we throw a die, let A1 be 1, 2, 3, A2 is 4 and 5, A3 is equal to obtaining 6. Thus, A1, A2, A3 are mutually exclusive, and A1 union A2 union A3 is equal to omega. Let A be the event that the outcome is an even number. Therefore, by the above theorem, probability of A is equal to probability of A given A1 into probability of A1 plus probability of A given A2 multiplied by probability of A2 plus probability of A given A3 multiplied by probability of A3 is equal to probability of getting an even number given that A1 has occurred, that is 1 by 3 because there is only one even number out of 3, multiplied by probability of A1, that is half, plus probability of A given A2. So, here we can get that there are two possible values and one of them is even. So, that probability is half multiplied by probability of A2, which is going to be 1 by 3 because occurrence of 4 or 5 is 1 by 3 plus there is one number 6 which is even. Therefore, this is going to be 1 multiplied by probability of A3 which is going to be 1 by 6 is equal to 1 by 6 plus 1 by 6 plus 1 by 6 is equal to 3 by 6 is equal to half, which is probability of an even number. Let me give you another interesting problem. A bag contains 10 white balls and 20 red balls. Balls are drawn at random without replacement. A, what is the probability that first ball drawn is white, B, the second ball drawn is white, and C, the third we have seen that after the first ball, since it is without replacement, the probabilities keep changing. Then how do we compute this probability? So, we shall solve them. For that, let me draw this diagram. Here the situation is 10 white and 20 red. After the first ball is white, I get 9 white and 20 red, and if I draw a red ball, then we get 10 white and 19 red. So, what is the probability? In this case, the probability is going to be 1 upon 10 upon 30, is equal to 1/3. In this case, the probability is going to be 2/3. After this, we are drawing the second ball, which may be white, which may be red, and if it is a white, the configuration becomes 8 white and 20 red, and this probability is going to be 9/29, and if a red ball is drawn, it is going to be 9,19, and this probability is going to be 20/29. Similarly, from here we will get 9,19, and that probability is going to be 10/29, and from here we are going to be, if it is a red, then we are going to get 10 whites and 18 red, and that probability is going to be 19/29. Now we are drawing the third ball. Then what we are going to get is 7, 20, and that probability is 8/28. If it is a red, we are going to get 8,19, and that probability is going to be 20/28. Similarly, if this is a white, that is going to be 8,19, and that probability is going to be 9/28. If this is a red, this is going to be 9,18, and that probability is going to be 19/28. If this is a white, we are going to get 8,19, and that probability is going to be 9/28. This is going to be red, that probability is going to be 19/28, and we are going to get 9,18. And similarly, from here, if it is a white, then the configuration is 9,18, and that probability is 10/28, and similarly for red, it is going to be 10,17, and that probability is 18/28. So, this is the picture. Therefore, let us now calculate probability first ball is white is equal to, as you can understand, this is going to be 1/3. Probability second ball is white, therefore, its probability is, by the earlier theorem, probability of white given first ball is white multiplied by probability first ball is white plus probability white given that the first ball is red multiplied by probability first ball is red is equal to, so probability of white given the first ball is white is equal to 9/29 into probability first ball is white is equal to 1 by 3 plus probability second ball is white given first ball is red is equal to 10 by 29 multiplied by probability the first ball is red which is equal to 2 by 3 is equal to 1 by 3 into 9 by 29 plus 20 upon 29 into 1 by 3 is equal to 1 by 3 into 29 upon 29 is equal to 1 by 3. This is same as the probability that the first ball drawn is white. Check that probability third ball drawn is white will also be 1 by 3. I have given you the base diagram. We have to make use of this diagram to find out that even in the third draw, if you are getting a white ball, then that probability is going to be 1 by 3. Okay, friends. Now, let me state a very important theorem which is called Bayes theorem. In reality, we often come across a situation when something has happened and we want to ascertain the cause behind it. So, this is a very, very practical situation. Say for example, a small crime has happened. Police wants to find the culprit. Let the above event be B. That small crime has happened. Now, police knows there are n persons A1, A2, An who might have committed the crime. And no one else can do it. Let AI be the event that person I has committed the crime. Therefore, let A be the event the crime has been committed then A is equal to A1 union A2 even An, and these are mutually exclusive, and exhaustive. That means there is no other way that the crime has happened. Now, we need to compute for each I what is the probability that the ith person has committed, or we want to know probability of AI given that the crime has happened, that is B. So, we are looking at probability that AI has committed the crime given something has happened. So, such probabilities are called a posteriori, because we are looking at the probability after something has happened. Now, police has the following information that probability of AI, let us interpret as probability ith person in the spot at that time and probability of B given AI that ith person commits the crime. Probability B given AI for different AIs are called their a priori probabilities. This is because they give the probability of the event B given that or on the condition that AI has happened, or in this context that AI has committed the crime. Hence, these are called a priori as they help in modeling the event with prior knowledge, that is, knowledge that we have before the event that has happened. On the other hand, a posteriori probability allows us to find the probability of different causes that might have been the reason for the occurrence of the event. Note that to compute probability A I given B, that is the posteriori probability, both probability of A I and probability of B given A I, which is the a priori probability, are important. Why? So, for illustration, suppose there are two suspects, A1 and A2, who might have committed the crime B. Now, suppose A1 has high probability say 0.9 of committing the crime B. On the other hand, suppose A2 has a smaller probability say 0.7 to commit the crime B. But on that day, A1 has a very small probability say 0.1 of being in the spot of crime. But for A2, this probability high, say 0.8. Therefore, we need to take care of both of them, these probabilities, to obtain the different a posteriori probabilities probability of A1 given B and probability A2 given B. Hope the concept is clear. Then Bayes' formula for computing the probability of AI given B is probability of B given AI multiplied by probability of AI divided by sigma probability of B given AI into probability of AI, I is equal to 1 to n. Why? Because we know probability of AI given B is equal to probability of AI intersected with B divided by probability of B. Also, this we can write it as probability B given AI multiplied by probability of AI divided by probability of B. This we get by exchanging the role of AI and B. And probability of B, we know that because AIs are disjoint event, therefore, some time back we have seen this formula that probability of B is equal to probability of B given AI into probability of AI, that we are summing from I is equal to 1 to n. Thus, from known probabilities we can compute a posteriori probability. Let me give an example. Suppose a student is writing an MCQ test. Each question has 5 options. So, if the student knows the answer, he will tick it correctly. If he does not know the answer, he will choose one of the 5 options at random, which we may say he is guessing. Now, suppose we know P is the probability that student knows the answer and 1 minus P is the probability that he guesses. Now, the question is, given a student gave the correct answer, what is the probability that he guessed it? I hope you understand the question. Therefore, if you look at it, we are looking at probability of guess given correct answer. Therefore, using Bayes' theorem, probability of guess given correct is equal to probability of correct and he guessed divided by probability of correct and guess plus probability of correct and knows is equal to probability of correct given he guessed multiplied by probability that he has guessed divided by probability of correct given he guessed multiplied by probability of guess plus probability of correct given he knows multiplied by probability of knows is equal to, if it is a random, then probability of correct given guess is going to be 1 by 5 and probability that he guessed is 1 minus P. Divided by same thing 1 by 5 into 1 minus P plus, if he knows the answer then he will answer it correctly. So, that probability is 1, probability he knows the answer, that is P. Therefore, the answer is going to be 1 minus P upon 1 minus P plus 5 P is equal to 1 minus P upon 1 plus 4 P. Okay, students, I hope you understand the significance of Bayes' theorem. It allows us to obtain the cause behind an event when something has happened. For example, consider a factory that produces some item, say X. Suppose there are 3 machines M1, M2 and M3. Suppose M1 produces 100 items per hour and it has a probability of P1 which is say equal to 0.01, that the item produced is defective. Similarly, for M2, the hourly production rate is 200 and the probability that an item produced is defective is say 0.05. For M3, the rate of production is say 300 per hour and the probability of producing a defective item is say 0.03. Now, suppose after 1 hour of production, there is one item which is found to be defective. Therefore, factory owner wants to check which machine among M1, M2 and M3 has produced the defective item. It is a very natural question for the factory owner. Therefore, we are looking for the a posteriori probabilities probability M1 given defective, probability M2 given defective, and probability M3 given defective. As you can understand that from the a priori probabilities that we have given above, he can compute these three probabilities and decide in which order he will check the machines. So, I hope you understood. So, this is a very practical application of Bayes' theorem. Okay, students, I stop here today. In the next class, I shall start with random variables, which is most fundamental concept with respect to probability. Thank you.